Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. Welcome Xiaocheng, who is moderating the course here with me. So today we are going to really start diving into the material, into the math. It's going to be a theoretical lecture, but I'm going to drive you through it. I know you have different backgrounds. For some of you, it might be easier. For some of you, more difficult, but I'll make sure that everybody understands. Before I do that, I have a question for you. Check that you listened last time, so for the introduction week, to see if you got the most important idea of them all. So here's my question to you. You can either access it by going to the EduApp URL that you see here, eduapp.app1.eth.ch, or you can download the EduApp from one of the Android or Apple stores. So what is the name of the principle posited by Edgar Codd in 1970, according to which users should not be exposed to the implementation level of a database system? Is it decoherence, data integrity, strong data typing, or data independence? So we have a majority, and the majority is for data independence, and the majority is correct. It is indeed called data independence. It is really a fundamental principle that we have in the database world, that the users should not have to deal with all of the complexity of the implementation of the system. The only thing they should have to deal with is the dealing with tables or whatever shape of data they have to query. Decoherence comes from quantum physics. It's actually the name, you know, when quantum computers actually fail because the qubits interact too much with the environment. That's called decoherence. Data integrity has to do with it can be actually several things. It can be that you don't lose data or that the bits do not get corrupted. And you can also have integrity constraints that enforce some relationships in the data. Strong data typing actually comes from more the programming side, even though we also have data types in SQL. But data independence, this is probably something I'm going to say 100 times in this course. If you have one idea to retain from the course, it is going to be data independence. All right, so let me now switch back to the slides. One. Okay, so we are going to discuss the theory of data models, more exactly tables, because there's other shapes out there. We can have text that looks like, data that looks like trees, that looks like cubes, that looks like graphs, or that looks like text, which was quite a hype in the past few years with ChatGPT. But we are going to focus on tables today. So I told you that a model is made of two things. First, what does it look like, what we're dealing with? And second, what can we do with it? So what it looks like is what we'll focus on today. It's basically like this is a tables. This is a table, and then that's going to be in 2 weeks, the theory of the relational algebra, which is what we can do with it. Projection, selection, grouping, and so on. So this is where it gets really, really exciting, because this is really, just like in mathematics, you can have addition, multiplication, and so on. You can also manipulate tables with something that is very elaborate and beautiful. So why tables? Where I kind of motivated that last time, this is why. This is actually thousands of years old. comes from Mesopotamia. So this is a relational table. In fact, it's a lot like this if you kind of compare it to something more modern. But frankly, this gives the goosebumps that it's actually the same idea thousands of years later. This is why everybody understands tables. It's much easier to even understand by human beings than pie charts or any other kinds of plots. Tables is really one of the most natural structures that human beings can understand. My computer is complaining. Just have to make it happy by clicking here. All right. So this is Edgar Code. He's considered to be at the origin of the modern relational database systems, not relational databases, because as I said, that thousands of years old, but he's at the origin of data independence and how we make it all work on top of computers. So again, data independence is about this line here. In fact, this is what it's about. It's the split between here, the logical level, and here the implementation. And then you can swap it. You could implement actually a relational database system on top of a clay tablet. Would be much slower, but you could also do this. Or in big data, you do it on top of a data center. You know, there's many ways to do that. All right. So now, if we want to dive into the math, we have to first, whenever you model something, that's a thing that physicists do, for example, you need to think of what you want to model and on the very high level, what you want to achieve. So if we look on the very high level, how we could explain it to a primary school kid, how do we model that? Well, the first term that we need is how to call it. So we tend to call it a table, but there's actually many other words that can be used a bit interchangeably. We can call this a table. We can call this a relation. We can call this a relational table. So these are all perfectly fine. Collection is more general. I come back to the difference between collection and table. So a table is a specific kind of collection, right? So this is what a table is. Then we can identify within a table, we see that it has rows and columns, right? So we can identify a row, and there's many other names for it. It's all synonyms, really. You can call it an item, you can call it a document, you can call it a record. I'm going to use the word records a lot today because it's kind of the most neutral way of calling it, but you can also call it tuple for other reasons that I mentioned today that has to do with the math. You can call it entity. There's something called the entity relationship model that's also taught computer science students. And the business people call it business object. That's kind of the coolest term you can imagine for that, but that's also what you might hear in the enterprise world. All right, so this is a row. Now you have the transpose of that, which is the column. It also has several names, several synonyms. You can call it an attribute. I use the word attribute a lot today. You can just say column. You can also say a field, a property, a key. That would be in the context of the JSON syntax, which is not part of this course, but this is also something you might hear, right? So table, records, attributes, and so on. So first name, last name, date, and so on. And finally, we have the concept of a primary key. A primary key is a way to identify your records. If you have a list of people, you can think of the social security number, right? The AHV-Nummer in Switzerland, which could be used to identify people. And you would then say that the AHV number is the primary key in a relational table that would contain the whole population, for example, right? These databases exist, actually. Have you heard of Serafe? Right. This is the company that has the mandate from the Swiss government to collect the TV fees, and they have a database of the whole population because they send over the mail every year. All right, so this is the primary key. Who is with me? Table, row, column, primary key. This is easy, right? That's just the high level. There's no math yet, right? This is just a high level description. Finally, we have the notion of value. So if you take a specific record and a specific attribute, that is going to give you a cell, a value, a scalar, a characteristic, a fact. So again, these are all synonyms of the same thing. I probably will use the word value or cell today. All right, so the intersection of records and an attribute, right? So we say that Mary is the value, associated with the attribute first in record number 4, right, with primary key PIDs 4. Okay, now this is what we'd like to achieve on the high level, but we have a bit of requirements of things that we would wish to have that would be captured by the mathematics model. The first thing we would like to capture is that the names of the attributes must be unique. You cannot have two columns that have the same name. In fact, if you try it, for example, in a spreadsheet program and you give two columns with the same name and you try to turn it into for filter data, I think it's called in Excel, then it's going to complain if you have two columns with the same name. So attribute names must be unique. In a relational table, you cannot have two attributes that have the same name, right? So this is not okay, for example. We have customer ID twice. That's not okay. You cannot have that. The second thing we'd like to have captured by the math is that the order of the attributes, the order of the columns, should not matter. Concretely, that means that the table you have on the left and the table you have on the right are mathematically the one and same thing. Although the order of the attributes is not the same. We have PID as first country, and here what happens is that we swapped, I think this is what happened, we swapped PID and first, right? But this is the same thing. That doesn't actually change the data that is in there, right? So this is also something that, that we would like. And we would like, some people would like, that's called the set semantics, we would like the order of the records to not matter. Imagine you have a relational table with the whole population of Switzerland, has 8 million rows. The order doesn't matter. Right? So you can list the population in any order. That's still the same data, right? So this means that the two tables here, which are only different in the order in which these people appear, here, you see the one is ordered by PID. The other one is actually probably not ordered by anything. I just shuffled them around, but this is the same table. Who agrees with that? Right? This is exactly the same data. So this is the same, this is the same. And now if you have the two of them, you swap the attributes and you also shuffle the records, the rows. This is also on the left and on the right, the exact same data. So if we come up with some math that defines what this is, we would like that math to consider this to be the same, right? Now, I put this set semantics in the parentheses over there, right? I said some people would like this to be the same. But there are also other flavors of the relational model with other semantics called the back semantics, for example, in which you do want to allow for the repetition of the same records. For example, here we have Srinivasa Ramanujan who appears twice and Marie Curie who appears twice, right? So in the back semantics, we also allow that. We also allow that records can happen multiple times, even though the order still doesn't matter, right? So this is called the back semantics. In the set semantics, that wouldn't happen, right? You wouldn't have several times the same records. In fact, since you have a primary key with a PID, that guarantees it, right? If you have the social security numbers and you only allow once every social security number, then you know that you're not going to have duplicate records, right? So in the set semantics, no duplicate records. In the back semantics, it's okay to have duplicates, right? It's just a different flavor. And finally, we have the list semantics. In the list semantics, we do care about the order. In the list semantics, these two are not the same, right? The first one is really 1, 2, 3, 4, 5, 6. The second one is 3, 2, 5, 1, 6, 4. In the list semantics, we do not consider them to be the same. Right? The three semantics are totally fine, right? So the way I would put it is that the original semantics of the relational model, and that's the one we will mostly discuss today, is the set semantics. I mean, you don't care about the order of the records and there's no duplicates. But if you look at the actual implementations, PostgreSQL, like all these database management systems in practice, that's true for Microsoft, for IBM, for Oracle, for PostgreSQL, for MySQL. In practice, they're all based on lists. I think the main reason is that in practice, you do need to order things. For example, imagine that you need to display web search results. Then you do need to return the first 10 records, right? You do need to order them in some way and return the first 10. So in practice, it actually does make sense to have to support some order and to care about the order. So in practice, the list semantics is going to be very common, right? But mathematically, it's actually the math really starts with the set semantics. Okay, so 3 flavors, set, bag, and list. Okay, so you can have sets of records, bags of records, or lists of records. So table is a set, a bag, or a list of records, right? So we are getting closer to the math. Okay, now a bit more of what we would expect from the relational model. We would like for the mathematical definition of a relational table to allow for an empty table, right? It's like the invention of the zero, right? It took actually a while for humans to come up with the zero, right? The concept of zero. And the same here, an empty relational table is totally fine, right? Just like in linear algebra, you can also have vector spaces of dimension 0, right? So, and so on and so on. So you do want to capture the special cases, because that rounds up the theory, right? It makes it more complete, and also for all the theorems and proofs that it's important to be complete. So you do want to accept empty relational tables. You also want to accept singleton relational tables. It means it's a relational table that only have 1 row, right? And of course more than 1 is also fine, right? So empty, singleton, and more is fine. Now, what about some other requirements that we might have in a relational table? There's actually 3 of them. 3 of them that I would say are required in 90% of the cases. In fact, in the 70s, they were strongly required. We only started to drop them in some cases in the 2000s with big data. And these 3 are domain integrity, atomic integrity, and relational integrity. Sounds scary, but I will show you visually what they actually mean, these 3. So let's start with relational integrity. Relational integrity means that the records that you have in here, how many records here? 3, exactly. We have Einstein, Ramanujan, and Gödel, right? So 3 of them. They all have the same attributes. How many attributes? 4, exactly. So they all have 4 attributes, and it's always the same 4 attributes, right? So you could even explicitly attach the attributes to the values like this. This is the same data. Here it's all glued together, and here we just repeat the headers for every record. But these are exactly the same. So this we call relational integrity. It's best to understand what it is with a counterexample. This is a counterexample of relational integrity that doesn't have relational integrity. Can you see what happens here? We have missing values. We don't have any value here in that second record for last. And here we don't have any records for physicists in the third one. And we even have an extra, sorry, we don't have any value. I think I said record. We don't have any value here, any value here. And here we have an extra value in that third record that is associated with country. Right. So this is a mess. You can see that it's much less structured than this one, right? So we say that here, relational integrity is broken. That is not a relational table. That doesn't even look like a table anymore. Okay. So that's relational integrity. So in my big picture here, it's this one here, right? Relational integrity. Okay. And you can see now I just display, so this is the one that's broken. Now, if I display the individual records, you still see that the records look like this. But now the records don't have the same attributes. So you can no longer glue them together in a way that looks like something like this, right? If you try to glue them together, you just obtain that, which is not as structured, okay? So this is relational integrity. Now, let's take a look at the second one. This is atomic integrity. It is also called the first normal form. We will see in a couple of weeks that there are other normal forms, right? The second one, third one, Boyce code, and so on. But this is called the first one because it's kind of a first level of requirements. Atomic integrity means that if you look at the values that are in that table, all of the values are so-called atomic values. So you can have numbers, dates, strings, and so on and so on. But now what does it mean, atomic, right? Well, it's better to show you a counterexample. This is a counterexample. So you see what happens here. Here, it's all atomic. And here, what do we have? We have tables in the table. I love to compare it. Who saw the Inception movie? Right? A dream in a dream in a dream in a dream. It's the same thing here. It's a table in a table in a table in a table. So if you have a table in a table in a table, then you break atomic integrity because the table is not atomic, right? So this has no tables in the table. This is fine. And this has a table in a table. So if you want atomic integrity, then you disallow tables in tables. So here I use tables, but more generally, you do not allow anything complex, any complex structures. That can be also something else than a table. That can be, if you know a bit of Python, an array, a list, a dictionary. Who knows Python? When I say list, dictionary. So you do not allow lists or dictionaries, for example, in the as the values. So again, strings are fine. These are strings. You also allow, these are all strings actually here, but you could also have numbers, you could also have dates, and so on and so on. Just no tables in the tables. No dream in a dream in a dream. Okay. I love the counterexamples because the best way to understand the integrity constraint is to see when they are broken, right? So this is the counterexample of the atomic integrity. Okay. So the atomic integrity, that was my second constraint. So now we have discussed this one here. We have discussed this one here, and now I need to explain the third one, domain integrity. So relational, here you go. Domain integrity has to do with what happens when you look at each column. You basically want that each column is homogeneous. You basically want to make sure that in the first column, these are all strings. In the second column, these are all strings. In the third column, these are Booleans. In the fourth column, these are years, integers, sorry. So this is called domain integrity. Domain integrity means that it is possible to fill the yellow line here with types for the data that is in there. If you can do this, if you can say in the first column there's only strings, the second there's only strings, the third there's only Booleans, the fourth there's only integers, then it means that your data fulfills domain integrity, right? Something important is that the yellow row here is not a record, right? It's why I put it in yellow. This is just an indication of the domains, of the kind of data you have in each column. For whom is that clear? Right? So there are still 3 records in there. Okay, that is a counterexample. That is a counterexample because you cannot do it in that case. You cannot put a yellow line with some types. You can probably see why. Here you have 2 Booleans, and here you have an integer, -1. Here you have integers, and here you have a string, right? So in that case, we break domain integrity. Now, some people can discuss and argue here. You could say, okay, yes, but what if we say, okay, physicist is a string, here is a string, and so on, and that kind of makes it work, right? But that's not the spirit of domain integrity. The spirit of domain integrity is really that there is a type that makes sense, right? So here, if you just say physicist is a string, you kind of circumvent the whole thing, right? It's kind of artificial. So you really would like to have Booleans or integers like in a way that is consistent, right? So this is the spirit. Who understands domain integrity, right? You have domains, type or domain. The yellow thing can be called type or domain, depending. Okay? All right. So now we have all 3. We have relational integrity, we have atomic integrity and domain integrity. And in short, if we have something that has a set of records, if it checks these 3 things, then we have a relational table. And we are in the beautiful world of SQL. And that's what's going to keep us busy. In this course, we will basically focus on that area. Then in Big Data for Engineers, if you come back in the spring, we're going to break the other rules and actually look at the space around here. Okay. All right. So that's called NoSQL, actually. All right, it's because of the real world, right? So basically, it's true that many times you can actually put your data in relational tables, but the real world is not like that. The real world is not as structured as this, and so this is why having some flexibility, especially when you start having billions of records, is actually useful. Okay, but this is the requirement level. Even though I started to be a bit specific, I did use mathematics terms like set, list, back. That's already a bit of math, but I still haven't said what a record is, right? On this, I still didn't really explain that. So let's try now to dive into some more math in there. What is a table mathematically? Well, I like to use the analogy with cooking, right? If you want to bake a cake or to cook something, then you start with the ingredients, right? And then you assemble the ingredients together. So what ingredients do we have if we want to bake a table, so to say? Well, we kind of have the attributes and the values, right? So these are kind of our fundamental things, right? So we have attributes, we have values, and the question is, how do we use a mathematical definition in order to assemble these attributes and these values to obtain a relational table? This is what we want to achieve. So in order to achieve this, I'll use some math. Some of you, it will be a walk in the park. You will know set, relations, functions, and so on. That has no secret for you. So maybe that will be a bit boring in the next couple of minutes. But some of you don't. And I want to make sure that everybody can follow, even if you don't necessarily have that background. So I'm going to take the time to really go through that. It's also a good refresher, you know, if you have heard about them, but maybe it's been a while. So let's do this. So the reason is really that this course is for all departments, right? So we have mathematicians, we have physicists, we have architects, we have weather and climate students and so on. So that's very, very diverse. All right. So this is a set. A set basically contains things. We can give names, right, in math. So we can call that A, written like this. A is a set. This is a set that contains 4 things, right? 4 items in the set. So what characterizes sets is that, so here's an example, I forgot. So this is the set of integers, natural integers, 0, 1, 2, 3, and so on. And then we have the set of strings. So these are all the texts that you can put in there. That's the set of a few strings. So this one is called n by mathematicians, right? N is the natural integers. I think 0, I don't know if we consider 0 to be natural integer, but that's the idea, right? N basically contains this, and star would be without the 0. Then S, so this is not used by mathematicians. This is what I use in this lecture. S is a set of strings. Strings are basically just sequences of characters, right? It's basically text. The empty string, I told you, right? We can have an empty table. We can also have empty strings, right? It's very common in computer science to put, and programming, to put the strings in quotes like this. So sometimes it's single quotes, here it's double quotes. This is basically something we do in computer science. The quotes are not part of the string. This is just to delineate the string, but this is just foo, F-O-O. The quotes are not part of it. Okay. Now, when we have a set, we in fact have a relationship between the set and its members. And the way we write it is that we call X, so X is this one here. We say that X belongs to A. X is in A, and we use that symbol right here. It sounds a bit trivial, right, or a bit simple. Do not be misled by the apparent simplicity. Set theory, I think, became really mature in the, let's say, in the 19th century, maybe. I mean, we always considered sets even previously, in the previous centuries. But I think that it reached the apex in the 19th century. And the point to which it reached the apex in the 19th century is that mathematicians committed suicide because of that. Just to say how complex that was. The reason was that you can consider sets that are infinite, right? Like the sets of all numbers, real numbers, complex numbers, and so on. Then you can have situations in which a set can contain itself, right? The set of all sets, for example, you have a set that contains all sets. So the set of all sets is also a set, so it should also be a member of itself. Then you can consider the set of all the sets that do not contain themselves and start to run into all of these weird situations that just break the whole thing, right? And so in the 19th century, at some point, there was this idea that we could start to be more mechanical in the way we do math, right? We can derive theorems in a more automated fashion, right? We can automate the theorem proving and derive with rules all of the theorems. And then somewhere in the 20th century, people realized that that actually doesn't work and things break. And you might have heard of the Gödel theorem, right? Completeness theorem. So this was where the whole thing collapsed, and we realized there cannot be a set of all sets and so on. We had to use other tools like categories to deal with that. So just to tell you, it looks simple. Do not be misled by that. This is in fact very complex, and you can have a lot of very, very heavy math and people who got Turing awards and all kinds of awards for these things. But of course, we are not going to go that far. We are dealing with computers, so it's going to be finite data. So if it's finite, then we don't have to worry about these things. All right. So I hope this history parenthesis was interesting to you. All right. So here, for example, we say that 1 is an element of n, of the set n. Foo here, the string foo, FOO, is an element of this set. Okay. Then we have another relationship between two sets that says that a set is a subset of another set. We say that we have a subset when visually it looks like this, right? It's included. It's an inclusion relationship. So it means that if you have something that's a member of B, then it is also a member of A, right? There is this implication. Then we say that B is a subset of A. So in the English-speaking world, we use the subsets together with an additional line. Not everybody does that. I know in France, for example, or French-speaking places, they only write this to also allow for equality. But in the English-speaking world, typically, if you say that, that's a strict inclusion. So there has to be elements that are not. And then you add this little bar to say it's a subset or equal to it, right? In LaTeX, it's subset ek, I think, the symbol. So this is a subset. For example, we can consider the set of even numbers, and that set is a subset of the set of all non-negative integers. Okay, who is with me so far? Who finds it easy? Okay, good. All right, another example is that if we consider a set of university names, like ETH Zurich, Stanford, MIT, PFL, NUS, and so on, Tsinghua. So this set of universities is a subset of the set of strings. That's another example that starts looking more like data, actually. Okay. Some of the sets are actually quite standard. In math textbooks, you will very often see B, that is the set of Booleans. It really has two elements, true and false. But even though it's simple, again, you can get very complex things. And again, logic, higher order logic, it's very quickly complex. D is for decimals. Decimals are numbers that you can write with a finite number of digits, right, in base 10, right, decimal 10. So all the ones you can write with a finite number of digits. N is the non-negative integers. V would be if you include the negative integers. S, that's not official. That's in my lecture. I use S for strings. That's also not official. I use V for values, but typically I mean atomic values, but doesn't have to be. You can also use it for any value, like anything you can put in a cell, in a table. And T I use for relational tables, right? I was tempted to use C for collections, but it's also for complex numbers, so I didn't want to do that to not bring confusion. All right, so these are some of the common sets. Okay, so let's back to this. Now we have sets that contain things. There are no duplicates in sets. The reason there's no duplicates is just that the math with this symbol is in doesn't capture the notion of duplicates. There's no way to express that. So sets do not have the notion of any duplication in there. If you want the duplication, that's a word I used earlier, it's called a bag, right? In a bag, you can have multiple occurrences allowed, right? So here, for example, you have a repetition of the same elements here, and you do have that notion of counting the number of times that an element appears in a set, okay? Then it's called a bag instead of a set. And then you have lists, set, bags, list. Lists can have duplicates, but they also have an order. There is a specific order in which this appears. So first green, then blue, then orange, and so on. There's many other names for that. Mathematicians also call them sequences. You know, when you have a list like that, you basically have the notion of the first one, the second one, the third one, the fourth one, right? Typically, you might have seen it as U subscript 1, U subscript 2, and so on when you have mathematical sequences. In computer science, we don't really call them sequences, we call them lists, right? Like in Python also, it's called a list. Array might be another term that you might see in computer science, right? But really, keep in mind these three: set, bag, list. This is really a triple. They go together, right? This is basically set, no duplicates. Bag, you have duplicates, and list, you also have an order in there. Okay. Okay. So if everybody with me, let's push it a little bit more. Let's build pairs. A pair is basically made of two values. I connect them here with this line in the middle. It's made of two values picked from two sets. One set from which we pick the value on the left, and one set for which we pick the value on the right. Right. So you can see it as a list of two if you want, but technically you call it a pair. We use this notation for it's called the Cartesian product, this cross here, due to René Descartes, because that was basically meant as the Cartesian product, for example, between the x-axis and the y-axis, gives you the whole plane, right? But in that case, A and B can be anything, right? So the Cartesian product of A and B contains all the pairs that you can build from one element of A, one element of B. And then I can say that if P belongs to the Cartesian product of A and B, then that's a pair made of an element of A and an element of B. And visually, that looks like what is displayed here. If this comes from A, this comes from B. Whom is that clear? Okay, that's called a pair. This is an example. If I take the Cartesian product of the set of strings and the set of non-negative integers, then ETH Zurich 20,000, maybe that was confusing here. I should remove that comma. This is the comma that separates the pair. Here it's just 1,000 separators. Maybe I should remove it, right? So like this, we have ETH Zurich and 20,000. That's made of two elements. This is a pair that is taken from the Cartesian product of S and N. Visually, I can put it like this, like ETH Zurich 20,000, okay? Maybe I should change it to 25,000 because I think now the number of students has grown again. When I arrived at ETH, I think there was 13,000 students. So now we kind of doubled the size. Okay. So now, more specifically, I told you a pair is a member of the Cartesian product between A and B. So let's draw that Cartesian product visually. So let's say I have a set A that has two elements, green and orange, and I have a set B that has two elements, red and blue. Then I can build four pairs, you know, green, orange, green, red, green, blue, orange, red, orange, blue, right? 2 times 2. It's basically the whole discipline of math is called combinatorics, and there's PhD students in combinatorics and researchers in combinatorics. They count the number of combinations you can have, basically. So here, if you count the number of combinations between two sets, right? One here and one here, the number of pairs you can get is the product of the sizes, right? Imagine you had 6 elements here and 7 here, then you would have 6 times 7 possible pairs, and that's 42, right? So here we get 2 times 2, we get 4 different pairs. So this here is the symbol for Cartesian product, the same one used for multiplication. It's associative. What do I mean with that? Who knows what associative means? So basically, I'll come back to that in 2 weeks, but you can abstract the notion of addition, multiplication, all of these things. You can make it very abstract. That has actually been done from the 19th century onwards. When you do that, you have some properties that this can have. One of them is commutative. This is saying that 2 times 3 is the same times as 3 times 2, right? It kind of seems obvious just because we've been like, since primary school, we've been repeated that. But actually, if you ask yourself, why is 2 times 3 the same as 3 times 2? It's actually not that obvious, right? If your kid asks you that, why is it? Then you will realize it's actually not so easy to explain, right? But basically, that's called commutative. Associative means that when, for example, you have an addition like 1 plus 2 plus 3, it means you can start computing 1 plus 2, or you can start computing 2 plus 3, right? So the order in which you basically add the numbers. If the order doesn't matter, you can add them in any way you want. That's called associative. That implies basically that the Cartesian product can be on more than 2 sets, right? You can have 3, 4. That's no longer called a pair. It's called a tuple, like this. For example, this is here 4 different sets. So we call it a tuple, a 4-uple, if you want, with 4 of them. And when I say it's associative, I basically mean that you don't have any notion of this first or this first or this first. It's just the 4 of them. There's a first, a second, a third, and a fourth. That's what we call associative. Now, I once got an email by a student who disagreed with me, and I agree that they disagreed with me, because if you are a mathematician and a purist, then you will argue, no, okay, it's actually not associative. But for the purpose of the course, it is associative, again, in the sense that we consider a tuple to just be a list of 4, in that case, a list of 4 values. The first one comes from A, the second one from B, the third one from C, and the fourth one from D, and it's flat, right? Okay, so this is the Cartesian product. Okay, here's an example. If I have a set of universities, let's see just 3 of them, and then the Booleans, that's 2. How many combinations do we have? 3 times 2 gives us 6. So we can build these 6 pairs. And that's the Cartesian product of universities and the set of Booleans. Now, again, we generalize to tuples. So it works with 2, with 3, with 4, with any number actually of sets. And you can build tuples from this Cartesian product of sets. We only consider finite numbers of sets, so it doesn't go to infinity. Again, if you go to infinity, this is where you become crazy, because that really involves so many complex things that start happening if it's infinite. But that's always a finite tuple here. Okay, this is an example of a tuple, a 4-uple, right? A tuple with 4 values that is taken from the Cartesian product of S, 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 and N, right? So we have a string, a string, a string, and a non-negative integer. So that thing here is a tuple taken from that Cartesian product. Who is with me? Okay. Don't worry, we are getting to relational tables, right? It looks like we're doing something completely different, but we are going to land on the relational tables in the end. You probably see it coming. I mean, you maybe start seeing it here. Is there oh yeah, that works. Sometimes maybe I'm too far away from the computer. It doesn't react anymore. I'm sure I loaded the batteries before coming, so it's supposed to. Okay. Now, so we have sets, bags, lists. We know the notion of pairs and tuples, Cartesian product of 2 sets. Here's yet another one. That's called a function. A function associates elements from a set with elements from another set, right? But in the way that every element from the left gets associated with exactly one element from the right. So we say we have a function here from set A to set B, right? So you see that the arrows in here, it's a visual way of basically show the function. This is associated with this. This is associated with this. They're both associated with yellow, but that's fine. This is a load. Green is associated with this. Blue is associated with this. So every one of these elements here has exactly one arrow that comes out of it, and it goes somewhere into B, and that can be anywhere. You can have some that have multiple arrows incoming and some with none at all, right? This is entirely fine. We say that F, this here, is a function from A to B with this little row. So this is the set of functions from A to B. You will also find this in literature. It sounds a bit fancier, but it's the same thing really. But it's more compact. This is the set of functions from A to B. So if this confuses you, that just use this one. Right? It's really exactly the same thing. These two notations. Okay. Mathematically, we use this to say that, for example, green is associated with purple or blue. I cannot see well. We use this to denote this association. Do not confuse these two arrows. This is between two sets to express the set of functions. This is between values, this value associated with this value. Okay, let's have a break. And then we'll continue in 15 minutes at 11:15. If you're not too scared yet with what I showed.